Okie dokie, number 42. We connect a battery, a resistor, and a capacitor as shown in this beautiful figure that I have copied from 26.20a.
It's so beautiful, Kelly. You're the best teacher ever.
There's also other people here. Alright, so R equals 12 ohms, C equals 5 microfarads, and the switch S is closed at T equals 0. When the current in the circuit has magnitude of 3 amps, the charge on the capacitor is 40 microcoulombs. Part A, what is the EMF of that battery? So this is going to be a super simple example of a Kirchhoff loop. So we have a nice current coming through here, whoop, 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 whoop. And that's going to be our I, and we're going to choose to take our loop in that same direction because it's the most convenient. Alrighty, so if we follow our loop, we go ba-doop, we gain some EMF. Now we're going with the current through this resistor, so we are losing I times R. Oh, but our I is 3 amps. How convenient they told us that. It's so nice. And then we go across this capacitor. Bloop, bloop. So if you remember, the voltage across a capacitor comes from Q equals CV. So V is Q over C. Our Q is 40 microcoulombs and our C is 5 microfarads. And that all has to equal 0. Huzzah! So micro cancel. So we have E minus 3 times 12 is 36 volts. 40 divided by 5 is 8. Yes. 8 volts. I can't do math. What's 36 plus 8? 44. All right, sweet.
Numerical.
So our EMF is 44 volts.
That's why you do everything with algebra, kids.
Adding is hard. All right.
Numbers are the devil.
They are the devil. Numbers are super the devil. Why did I decide to do these at home? This is a terrible idea. Okay, so for part B, we want to find what time after the switch is closed is the charge on the capacitor equal to 40 microcoulombs. So there we're going to use our current through an RC circuit equation. And that looks like so. So it's an exponential decay, where I naught is the current through the circuit initially. So when we first start out, we have our switch, we have our resistor, our capacitor, and our battery, right? So when you first close this switch, current is just going to start blasting through this circuit. So charge, as soon as you first close it, is not going to be collecting on this capacitor. So as soon as you close it, all the current is just like, woo, all the way through. Your capacitor is acting like a wire. Then it's going to start accumulating charge. And the current is going to start exponentially decreasing. So at first, this looks like a wire. So a wire at T equals 0. Okay? Which means we can get the current that we start with through good old Ohm's law, V equals IR. So over here, the current at any given time T is I naught, which is going to be V over R, which is in our case EMF, over R, e to the minus T over RC. So now we want to solve for T. So we're going to multiply R divided by E. So we have RI over E equals e to the minus T over RC. Now we want to get rid of this exponential, so we log both sides. Log. So the natural log of Ri over EMF is equal to minus T over RC. So T is equal to minus RC log Ri over EMF. So R is 12 ohms. C is 5 microfarads. Natural log, 12 ohms. I, at the point we care about, it said was 3 amps when the charge was 40 microcoulombs. So that was one of our givens. And our EMF we found to be 44 volts. All right, so now we can plug this into our handy dandy calculator, which still belongs to Michelle Zhang. If you know who she is, please tell her I have her thing. Come get it, for the love. So 12 times 3 divided by 44. Natural log of that stuff times 5 times 10 to the minus 6 times 12 times the minus 1. So 1.2 times 10 to the minus 5. So 1.2 times 10 to the minus 5 seconds. Okay, so for part C, when the current has a magnitude of 3 amps, at what rate is energy being I stored in the capacitor and double I supplied by the battery? So power is defined as du dt. So here we can't just say energy divided by time because our energy is time dependent because we have an RC circuit. So the time derivative of the energy we can write in terms of Q. So one of the ways we can write energy is Q squared over 2C. We can also do 1/2 CV squared, any of those guys. But in this case, it's easier to do Q. All right, so the time dependence in this circuit is living with our Q. So 2 and C are constants, so we can pull them out. Then we have the time derivative of Q squared. So our time dependence is hiding in here, so that means we need to do a chain rule. So if we do that, we have our 1 over 2C constants. Derivative of Q squared is 2Q. And then my chain rule is going to give me a dQ dt. Okay? So time is hiding inside Q. So first I have to take the derivative of this to get 2Q. And then I have to take the time derivative of Q to get that out. So my 2's cancel out. I get Q over C dQ dt. Now, fun fact here, dQ dt is the definition of current. So that is current. So the power as a function of time through this capacitor is Q over C times I of t. Okay? So Q at the time I care about is 40 microcoulombs. My capacitance is 5 microfarads. And my current at the time I care about was 3 amps. So if I plug that in, that's going to give me a power of 24 watts. Okay? So that's the power in the capacitor. Now the power through a battery is just P equals IV. So the power here, the time dependence is living in the current, but we don't have any derivatives or any of that nonsense going on here. So the only reason we had to deal with derivatives here is because we had current as a function of time, which means our charge was changing as a function of time. Here, P equals IV, we can just multiply the things together. So our I is 3 amps, and our voltage was 44 volts. So that's 132 watts supplied by the battery.